can imagine that falling film reactor ni in a tube, okay, vertical tube, and then the liquid will form a film on the wall of the tube, and then the gas flow in. Then mass transfer from gas phase to liquid phase occur, and then for the case of catalytic wall reactor, so the reactor becomes three phases reactors where we can conduct the three phases reaction. Okay, so but you cannot imagine the size. So actually for falling film, dia bentuk pipeline, okay, small pipeline. So that's why we have the problem. In order to increase the yield of the reaction, because for small size of tube to conduct the reaction, so only small product capacity that we can produce. So that's why to design the efficient falling film reactor ni, it is difficult lah. Okay, so that's why we need another type of column, large column, that we can conduct for the different phases of reactants. Okay, so it can be accomplished with rising bubbles or falling drops. So rising bubble yang we can call it as a bubble column reactor. So falling drop, spray tower, because the falling drop ni referring to the liquid reactant. Okay, liquid drops. Rising bubble, gas bubble. Falling drop, the liquid drops. Okay, so when and how does bubble column reactor works? Okay, normally use for reaction where the gas-liquid reaction is slow compared to the mass transfer rate. So the purpose of this bubble column is to increase the mass transfer between gas and liquid. Okay, so if we consider that the reaction only occur in liquid phase, so we need to increase the mass transfer of gas to liquid phase. It is widely used in oxidation, hydrogenation, and alkylation process. So oxidation, hydrogenation, and alkylation are the example of multi-phase reaction. So gas bubbles introduced at the bottom. So if you look at the bubble column here, so the gas bubble from the bottom, the liquid already fill in the tube. So this is the tube of reactor vessel. So the bubble rise, the gas separated from the liquid in the head space, and pure liquid is withdrawn at the bottom. So this is for the product. Okay, so liquid here is the product. But this liquid is reactant liquid. So gas, reactant gas introduced from the bottom, and the product at the head space at the top of the vessel. Okay, so this is the bubble column. So compared to a spray tower, so what is the difference between bubble column and spray tower? Spray tower, the vessel is filled with the gas reactant, okay, and then the liquid introduced from the top. And how we introduce the liquid, so in terms of drop. So this is the liquid drop, and it will accumulate at the bottom, and this is the liquid product withdrawn at the bottom. Okay, and gas here, this is the product after the reaction. So this is the outlet of the gas product, ataupun kalau tak ada product, the remaining gas from the reaction. So that's the difference between bubble column and spray tower. But the concept is similar. The concept, how it works, okay, how the reaction in bubble columns works, it's similar with spray tower. Okay, so the problem now, when we have the bubble column, how to control the size of this bubble and the size of liquid drop. Okay, so but before that, we need to know how the reaction will occur in this type of column. Okay, for both bubble column and spray tower, reactant A must migrate from a drop or bubble into the continuous phase to react. So which one is continuous phase? So if the reaction occur only in liquid phase, so the bubble gas, okay, will migrate from the bubble to the liquid phase. So kalau kita tengok kat sini, so the bubble ni, bubble gas will transfer to the liquid phase, absorb in liquid. So dia, your reactant A, gas A tadi akan jadi liquid. So how to calculate the concentration of gas reactant in liquid phase? Again, by using Henry's law equation. Okay, as I shown in the previous class. Okay, bubble columns rely on nozzles, mixing plates and impellers within the reactor to control the bubble size ataupun to control the drop size. So to control the bubble size for gas and to control the drop size for liquid. So it will provide the high area and small particle size for high rule. Okay, so we assume all particles have the same size, and the disadvantage of this bubble column ataupun disadvantage of gas bubble and liquid drop, the coalescence that will drop the surface area. So when there's a lot of liquid drop and gas bubble, so the
Slide Doktor tak gerak.
Tak gerak.
Stuck dekat slide number 24.
Sampai sini je. Sini nampak?
Ya. Yeah.
Allah. So yang ni belum nampak.
Tak nampak.
Ni tadi, ni sekarang nampak?
Sekarang nampak dah.
Sekejap, kalau saya try project.
Boleh cuba.
Nampak tak? Saya tengah project.
Tak nampak.
Oh, tak nampak. Okay, saya stop dulu. Okay, try share balik. Try share lagi sekali. Stop sharing. Okay, nampak ke tak? Gambar bubble column and spray tower.
Nampak, tapi boleh tak Doktor cuba tukar slide nak nampak kalau gerak atau tak.
Okay, now? Gerak tak?
Tak gerak. Dia masih dekat bubble column.
Still gambar bubble and spray tower. So bila saya
betul.
gerak, dia tak keluar.
Ya, betul.
Ayo. Apa ni apa maksud dia? Ni apa?
Mungkin Doktor tak perlu nak.
Tak payah ni lah ya. Tak payah full screen.
Betul.
Okay, saya besarkan saiz dia
Okay, betul.
So yang ni yang tadilah saya explain balik lagi sekali lah.
Okay.
cantikkan. Right. So nampak kalau macam ni?
Nampak doktor.
Alright. So tak payah guna ni lah. Okay, so yang ni tadi bubble column, spray tower. So bubble column, gas dalam bentuk bubble. And for spray tower, liquid in drops. Okay, liquid ni fill in the tube, okay, ataupun tube vessel in as a drop. So that's the difference between bubble column and spray tower. So yang ni tadi yang saya cakap how the mass transfer occur. Okay, reactant A migrate from a drop or bubble into the continuous phase. To react continuous phase ni kalau reaction occur in liquid phase. So the continuous phase is the liquid itself. Okay, and then bubble columns rely on nozzle, mixing plates and impellers within the reactor to control the bubble size for gas and drop size for liquid. So it will provide the high surface area and small particle size where the reaction can occur. And we assume all parameters, we assume all particle, okay, drop, gas bubble and liquid drop have the same area. So the disadvantage tadi, the bubble or drop collision will drop the surface area. So if you look at the bubble column and spray tower here, so kalau drop, liquid drop ni, berlaku pelanggaran sesama sendiri, it will reduce the surface area where the reaction between gas can occur. So similar for bubble gas. So tadi tak nampak gambar. So saya tunjuk balik. So bubble column, gas introduced from the bottom, and then yang ni, yang tiga nak panah, this is where you where you arrange the nozzle, where you design the nozzle to control the size of the gas bubble produced when the reaction occur. Okay, and then reaction berlaku, liquid ni we fill in before we introduce the gas. We fill in the vessel before we introduce the gas, and then after introduce the gas, reaction occur, and then the product released from the ataupun withdrawn from the bottom. Liquid here is liquid product. Liquid yang ni liquid reactant. Gas here, the remaining gas or the product. Okay, either one. Okay, sometimes boleh jadi the reaction will produce product in liquid phase and also in gas phase. So kalau ada product in gas phase, so dia akan the outlet stream is at the top. For spray tower, the vessel consists of gas reactant, okay, and then we introduce the liquid drops from the top. So dia masuk as a drop and then withdrawn at the bottom, they accumulate at the bottom. So when the reaction occurs, so sepanjang ni, from the first drop at the top until the bottom, so the reaction will occur. So maksudnya bila dia dah accumulate at the bottom of vessel pun reaction can be occur because the column is consist of gas. Okay, we fill the column with gas before we introduce the liquid. Okay, now we look at the reactor design. So actually, reactor design for bubble column ni much more simpler compared to falling film reactor. Okay, so first we look at the size. Yang ni if we consider, usually we will use this equation if the reaction in bubble column is mass transfer limited. So if the reaction in bubble column is mass transfer limited, we will apply all this equation. Okay, so bubble phase volume occupy void fraction. So this is how you can calculate the volume of gas, but you need to know the void fraction, the total void fraction, okay, multiply with the V. V here is total volume of reactor. Yang Vg ni only the volume of gas phase. And then volume of each bubble. So of course lah kalau tengok the formula, volume of each bubbles ni the volume of spheres. But this is for one bubble. So you need to know how many bubble produced inside the vessel. So kalau macam ni, we need to estimate how many bubbles can be produced from one run of reaction. So barulah kita boleh calculate the mass transfer, total mass transfer occur in the reaction. Assume that all particles have the same size. So kalau if you know what is the concentration at the surface and also concentration at the bulk fluid, okay. So this is the mass transfer flux. So if you look at this equation, area 4 pi r square ni the area multiply with the mass transfer flux. So this is the equation. We can simplify it. So Ca here, concentration at the bulk fluid minus concentration at the surface area. So kalau tengok ni and then you relatekan, ada pula integration that we need to integrate based on the size of the bubbles. So kalau tengok dekat sini, from this equation, single equation ni pun dah quite complicated. And usually for bubble column, we rarely assume that the mass transfer will remit direction. We assume that the reaction biasanya very fast, the mass transfer very fast. Therefore, the reaction limiting the overall system ataupun the reaction controlling the system. Okay, so nanti saya tunjuk contoh. Okay, but before that, kita tengok dulu ni apa. Okay, dah nak habis dah pun. Tinggal, so this is the last slide. So yang ni kalau falling film catalytic wall reactor. So yang ni saya dah tunjuk juga dalam kelas, saya dah ada draw. What's the difference between the falling film and falling film catalytic wall reactor. So kalau catalytic wall reactor, the catalyst, the reactor consists of catalyst on the wall ataupun on the wall of the vessel, falling film vessel. Okay, yang ni kalau for three phases reaction. Right, so dah habis. So now we look at the example of bubble column. Mana dia? Okay, ni falling film. Right. So contoh, alamak dia punya ni hilang. Tak boleh edit. Itu enable editing. Ini sebenarnya anak panah. Baik. Apa tak boleh jadi besar nak masukkan anak panah? Boleh. Okay. So this is the reaction. So macam mana nak tahu dia bubble column? Okay. Usually there's a hint in the question. So a liquid A in a solvent is being hydrogenated by bubbling. So automatically we know that this is bubble column. At bubbling H2 at atmospheric pressure through the solution to form another
Doktor.
liquid B. Ya?
Doktor tak share screen.
Ha? La ilaha illallah. So yang tadi yang catalytic wall tadi nampak ke tak?
Catalytic wall
nampak,
tu
Doktor.
sempat. Itu nampak.
Nampak. Bila bubble column ni tu tak nampak. Apa benda ni? Nampak tak? Soalan. Ke tak nampak?
Nampak doktor.
Ni nampak?
Nampak.
Okay. Alright. Okay, so a liquid A in a solvent is being hydrogenated by bubbling. So tahulah, this is bubble column. Okay, by bubbling H2 at atmospheric pressure through the solution to form another liquid B in the reaction A plus H2 produce product B. The column is 10 centimeter in diameter and 2 meters high, and the bubble rise with a constant velocity of 10 centimeter per second. The flow rate of the liquid is 15.7 centimeter cube per second. The gas bubbles occupy negligible volume in the reactor. Okay, so sebenarnya soalan ni soalan paling senang. Okay, sebab apa saya cakap senang? Okay, apa satu pula? Balik. Allah. Delete. Okay, sebabnya soalan dia, calculate the residence times of gas and liquid in the reactor. Yang ni should be no problem. Soalan paling senang. Because you have the height of reactor and also the diameter given. Bubble rise with constant velocity, yani velocity of gas, and the flow rate of the liquid, volumetric flow rate of liquid given. So the first question, calculate the residence time. Okay, let's say saya tambah ni, kita tengok. Okay. So kalau nak kira residence time, tau untuk liquid phase equal to, because we have the diameter. So you can calculate residence time for liquid phase as length or height of diameter divide with velocity. Sebab dia bagi velocity. Yang ni untuk constant velocity. Bubble rise with a constant velocity. Velocity ni for both gas and liquid kita boleh guna. Tapi sebab we need to calculate the ni. So kalau untuk gas phase pun sama. Okay, tau gas equal to L divide with, ya Allah, ni gas phase. Gas phase. Okay. Tapi sebab dia bagi velocity ni gas untuk gas, constant velocity bubble rise untuk gas, so kita tak boleh guna untuk liquid phase. Sebab liquid phase velocity not given in the question. Yang ada velocity gas sahaja. So length we have 200 centimeter, sebab dalam soalan ni 2 meters height. Page yang saya tengah tulis ni nampak ke tak?
Nampak.
Yang ni
Nampak,
nampak.
Doktor.
Okay. So sebab dia bagi height dia 2 meters, so it's equal to 200 centimeter divide with the velocity 10 centimeter per second. Yang ni residence times for gas phase. Okay. Tapi untuk liquid phase, because we can calculate the volume. Okay. Kalau tau L, it's equal to residence time volume of reaction mixture divide with volumetric flow rate. Volumetric flow rate given volume of liquid phase ataupun reaction mixture, we can calculate it by using the formula to calculate volume, which is volume of a cylinder lah, pi over 4 R square L divide with volumetric flow rate. Volumetric flow rate given in the question apa? 15.7. Bahagilah 15.7 centimeter cube per second. And then you will get the residence time in liquid phase. So kalau gas phase tadi, formula yang ni, which is equal to 20 second. So kalau untuk liquid phase, radius dia bagi tak? I think bagi 10 cm diameter. So R dia 5 cm. So ganti masuk je lah. Pi over 4 multiply with 5 square multiply with the length of rectangle, which is 200. So pi over 4, 5 centimeter square multiply with 200 centimeter divide with 15.7 centimeter cube per second. Then you will get the residence time in liquid phase. Okay, yang ni untuk question A. Okay, next, write the mass balance equation that would be used to solve the liquid phase concentration, CA, assuming that the rising bubbles stir the liquid and the reaction occurs homogeneously in the liquid with a rate of kCaCH2, where CH2 is the concentration of H2 in the liquid solution. So sepatutnya yang ni CH2, concentration of H2 in liquid phase. Ni sepatutnya ni nanti saya betulkan lah. Sudah. Later lah baru saya betulkan. So sepatutnya concentration of H2. Okay, concentration of H2 in the liquid solution. So dia dah bagi tahu dah dalam soalan. Reaction occurs homogeneously only in one phase, in the liquid. So reaction tak berlaku in gas phase. Rate equation given. Dia minta you buat, dia tulis mass balance equation je. Mass balance equation yang mana? Overall mass balance equation. Okay, overall general mass balance equation. Okay, and then another clue, rising bubble stir the liquid. Yang ni dia punya main clue. Okay, rising bubble stir the liquid. Apa maksud dia? So bermaksud we can model the reactor as a CSTR. Okay. Sebab ada stirrer. So rising bubble walaupun okay, if you look at the diagram of the reactor ni tadi, okay, bubble column, there is no impeller, there is no stirrer. Tapi rising bubble ni will act as a stirrer in the system. Okay, rising bubble with high velocity will act as a stirrer to mix the reaction mixture perfectly. So that's why we can assume that, mana pergi page soalan tadi? Hilang. Okay, ni dia. Okay, so the rising bubble ni with high velocity will act as a stirrer to form uniform mixing. Okay, untuk uniform mixing. So remember that bila you buat design project later, inilah knowledge yang you akan guna when you are in part 7, part 8 later. Okay, so kalau you need to produce the reaction that involve multiple phase reaction, so tak semestinya kena guna CSTR, reactor CSTR tu. So kalau you guna reactor without impeller pun, we can model it as a CSTR. Okay, for example, this case. So the rising bubble will act as a stirrer to form a uniform mixing between the gas and liquid. Okay, so reaction only occur in liquid phase. Okay, next, what you need to do, sebab dia kata write the mass balance equation. Negative Rg, okay, in gas phase equal to 0. There is no reaction in gas phase. Tapi in liquid phase, negative R equal to KL CAL CH2L. So this is the reaction, and because of that, because of ni tadi can be model. So usually you need to write the assumption of the reaction. So the assumption of reaction satu, no reaction in gas phase, reaction only occur in liquid phase. And then reactor ataupun reaction system can be modeled as CSTR. Therefore, the mass balance is CA0 in liquid phase, CA in liquid phase per tau L equal to KL CAL CH2L. Ni untuk menjawab question B. Yang ni. Dia kata write the mass balance equation. So this is the answer. This is the mass balance. And finally, question C, barulah calculate. It is found that the concentration of H2 in liquid solution, dia dah bagi siap-siap, tak payah guna Henry's law equation to determine the concentration of hydrogen gas in liquid phase. So this is the concentration of hydrogen in liquid phase. Okay, and then rate constant given K equal to 4, second order rate constant. Determine the conversion. So you have this mass balance. From this mass balance, okay, so dia bagi tadi concentration of hydrogen in liquid phase dah ada. You nak cari conversion sahaja. So how you can relate it with the conversion? So from this mass balance equation, relatekan dengan conversion. Of course, we know that concentration of A equal to CA01 minus X. So substitute this equation into the mass balance. Dapatkan equation in terms of conversion. And then determine the X. K given, concentration of H2 in liquid phase given. So therefore, it should be no problem for you to determine what is the conversion. Determine X. So just substitute CA as CA01 minus X. Similar for this one. Okay, rearrange the equation dulu, kemudian CA substitute as CA01 minus X, and then rearrange for X. So this is what you have learned in reaction engineering 1. Okay, so you apply balik. So that's why saya dah cakap hari tu for chemical reaction ataupun chemical part, we need to relate it with what you have learned in reaction engineering 1. So the basic, the fundamentals of reaction engineering 1. Okay, so dah substitute, rearrange for X, and then insert the value of K and concentration of hydrogen in liquid phase. Then you will get the conversion. Okay, ni soalan sebenarnya soalan paling senang. Okay. So yang ni susah sikit sebab yang ni dia involve STP. Yang ni calculation dia ni sikit. Ada additional. Okay. Next. Okay. Yang ni saya nak tunjuk. Dia tak bagi tahu pun type of reactor. Kalau falling film dia akan bagi tahu. Falling film senang dia nak tahu dia akan form a film. Itu falling film reactor. Tapi yang ni sejenis reactor biasanya memang bubble column or spray tower, tapi dia tak state pun in the question. Okay, sama ada is it bubble column ataupun dia spray tower. Tapi usually is macam mana kita nak predict the reactor tu can be model as a PFR or can be model as CSTR based on the condition of reaction. Okay, now page ni boleh nampak tak? Soalan lain ni.
Boleh,
nampak ke tak? Boleh Okay. So soalan dia sebenarnya yang ni similar dengan the previous question. Okay. Tapi dia tak bagi tahu bubbling ke drop ke, dia tak bagi tahu. Okay. So the reaction A plus B equal to product occurs in an unmixed flow reactor with B entering in the continuous aqueous phase and A in the organic phase. Reaction occurs by A transferring from the organic phase into the aqueous phase where the reaction occurs. So maksudnya A ni yang akan transfer to B. Yang ni berkemungkinan liquid-liquid phase with different density of liquid. Okay, so we still consider it as a multi-phase reaction. The organic phase forms drop. Okay, dia bagi tahu drop. So, either bubble column ke spray tower. Okay, forms drop. Allah, belum habis baca soalan dia gerak. Mana dia tadi? So, the organic phase forms drop 0.1 cm in diameter. And the flow rate of organic phase 1 liter per minute. Volumetric flow rate of organic phase. At initial concentration 2 moles per liter. The flow rate of the aqueous phase 9 liters per minute and concentration of B at initial equal to 1 mol per liter. Okay. Soalan ni sebenarnya senang je. Okay, cuma kita tak tahu whether either we want to model the reactor as a PFR or as a CSDR. Tapi hint dia dah bagi dekat sini. Unmixed flow reactor. So, bila nak jawab soalan, dia kata find an expression for the pseudo-homogeneous reaction rate in moles per liter per minute versus CA and B if the reaction is limited by mass transfer of A from the organic phase with the reaction instantaneous in the aqueous phase. Assume a Sherwood number of 2 with dA equal to 10 power of negative 5. So sebenarnya the reaction is limited by the mass transfer. Okay, mass transfer limiting. And then dia bagi Sherwood number. So Sherwood number equal to 2. Remember in chapter 1 when Sherwood number equal to 2, meaning that the reaction around spheres, around the drop tu lah. Okay, mass transfer around the drop. Okay. So how to answer this question? Sebab dia minta expression je. So, bila dia kata unmixed flow reactor ni, we can model it as a PFR. So, kalau tadi yang soalan sebelum ni stir dia bubble rise, stir the reactant. So, we assume it is uniform mixing. And that's why the reactor can be modeled as a CSDR. Now, unmixed flow reactor. So, kalau unmixed flow reactor, automatically we can model the reactor as a, apa tu? Ya Allah. As a PFR. So, how to answer the question? So, soalan B, what volume of reactor is required for 90% conversion? So, yang ni later. So, kita nak jawab soalan ni. When the reactor is unmixed flow, kalau unmixed, ya, kenapa keluar iklan? Ni. Okay. Soalan A. Sebab it is limiting by the mass transfer. Okay, sebab dia dah bagi tahu dalam soalan dia limiting by mass transfer. Manakah ayat dia tadi? If the reaction is limited by mass transfer of A from the organic phase with the reaction instantaneous in the aqueous phase. So, R equal to A over V R prime. So, this is the equation that we are going to use. Sebab dia dah cakap juga in the question. Mana pseudo-homogeneous. Find an expression for the pseudo-homogeneous reaction rate. So, this is the pseudo-homogeneous reaction equation. Okay. So, R equal to K CA CB and it's equal to A over V. R ni yang pseudo homogeneous, K CA CB ni, and it's also equal to A over V multiply with the rate of mass transfer, which is KMA, CA in bulk fluid. So, bulk fluid sepatutnya B lah. Kita nak bezakan B produk tu tadi. Minus CAB per 1 plus K prime per KMA. So, mana datang this equation? From chapter 1. Okay. You have derived it in chapter 1. And then define. Sebab dia dah bagi Sherwood number. KM equal to Sherwood number multiply with diffusivity divide with diameter. Sherwood number given equal to 2 dA. Okay. Diameter dia bagi tak dalam soalan 0.1 cm in diameter. Ada tak diameter lain diberi? Tak ada. Okay, drops dia 0.1 cm in diameter. So, D, okay, ataupun kalau tak nak masuk the value, you can write the diameter equal to 2R ataupun in radius lah. R here is a radius. So, it's equal to dA per R, radius. Okay, ataupun you want to leave it as 2 dA per D pun is okay. So, just define. Sebab soalan minta find an expression. So, this is the expression. As long as you define what is KMA. And then dA value given. dA value given, tulislah. It's equal to, dah tak boleh tulis pula dah. Then dA given as apa tadi? 10 negative 5 per centimeter. 10 negative 5 centimeter per second. Centimeter square per second. Centimeter square per second. Divide with, ganti masuk the diameter. Kalau tak nak jadiin radius, ganti masuklah 0.1 centimeter diameter. Ataupun kalau radius 0.05 cm. So this is the expression. Belum lagi nak buat calculation. Dia minta expression je. Okay, then next, what volume of reactor is required for 90% conversion? You have the equation ni tadi. Okay, equation ni A over V, KMA, CA, B minus CA per 1 plus K prime KMA. So, use this equation. Okay, KMA ganti masuk balik. And then this term yang belakang ni can be negligible. Yang ni kalau mass transfer kita tengok balik sebab yang limiting is limited by mass transfer of A from the organic phase. So in order to calculate the volume, tadi kita buat mass transfer of A because it's limiting by mass transfer of A. But in order to calculate apa value yang kita tak ada, K prime ni kita tak ada. K given in the question, tak ada. There is no K given in the question. No K value given in the question. So, kalau tengok data yang dia bagi, we just, we are only able to calculate KMA value because we have the diffusivity and the radius and also the Sherwood number. Tapi the problem, if we want to use this mass balance equation, we need to have this K value. K prime ni. Yang ni tak ada dalam soalan. So, how we are going to solve the problem? We can use the mass balance of B. Okay. Ataupun we can make an assumption that this term can be negligible because the value of K ni small. Kalau small, 1 plus ni, small bahagi besar ni 2 small, CAB. And then another problem is we don't have ni kalau term ni besar, ni kecil bagi besar, dia too small. So, we can solve it by using the mass balance of B. Kalau mass balance of B, boleh solve sebab we have both value. We have both concentration of A and concentration of B. So, kalau dikata what volume of reactor required, soalan B, volume of reactor, okay, equal to berapa? Determine the residence time dulu. Sebab yang ni PFR, reaction can be modeled as PFR. Therefore, dCB over dt, okay, based on B, disappearance of B, okay, sebab kita ada juga B. So, negative dCB over dt equal to A over V dA per R. Yang ni dah masukkan dalam mass balance equation KMA ni. CAL. CA in liquid phase sebenarnya. Pemadam. Tak ada pula pemadam ni apa? Eraser ke ni? Okay. CA in liquid phase. So, ada value. Determine, okay, B given, A given. Tu tak ada masalah. Determine P. Okay, determine T. And then, bila you dah determine T, calculate volume. Sebab volume equal volume divide with volumetric flow rate, you will get residence time. Multiply with volumetric flow rate. Okay. So, conversion given. Sepatutnya tak ada masalah lah. Conversion untuk A 90%. Conversion untuk B pun 90%. So, dapatkan T ni sahaja. Okay, cuma we need to know the reaction can be modeled as apa and what is the limiting. Okay, so again, this equation actually we derive from this one and term yang belakang ni negligible. So that's why dapat this equation. Lagi satu soalan yang lebih kurang sama. The beza dia mana hilang ni? A plus B equal to product. Okay. So yang ni pula hint dia well mixed. So kalau well mixed emulsion reactor bolkan. Maksudnya tadi kalau soalan tadi unmixed flow reactor. So beza dia unmixed flow, we can model it as a PFR. Kalau yang ni unmixed, mana tak gerak. Kalau yang ni well mixed, so it can be modeled as a CSTR. So can be modeled as CSTR. Itu je beza dia. Tapi mass balance dia sama. Mass balance, this is the mass balance. But when you want to solve the reactor design, dah tak guna yang ni lah. Gantilah dengan, so bila you nak kira volume of reactor, gantilah dia punya equation as CB0 minus CB per tau equal to A over V dA per R CA in liquid phase. So this is how you can solve the design problem. Okay, expression ni tadi untuk soalan A, expression dia sama dengan yang ni. Just you can write negative RA equal to CA0 minus CA per tau ataupun for species B, CB0 minus CB per tau. Okay, untuk expression. So expression negative RA equal to CA0 minus CA per tau equal to ataupun negative RB sama dengan CB0 minus CB per tau. And then for pseudo homogeneous reaction rate ni semua yang ni je. The same equation. Okay, use the same equation. Okay, soalan yang ni beza dia type of system je. Well mixed and unwell mixed. That's the difference. The rest sama. Okay, and then ada lagi satu, last one. Contoh untuk bubble column. So yang ni bubble column example ni nanti saya akan upload the video on how to solve this problem. Ini dah terang, dah explain dah tadi sebenarnya. Okay, soalan yang first tadi, inilah dianya. Okay, so nanti saya upload live juga balik sebab yang ni saya just explain dalam slide ni je on how to solve this problem. So nanti saya upload the video untuk soalan yang ni. Okay, so soalan yang ni saya tak ada video dia, cuma saya nak explain untuk unmixed flow reactor you can model at the equation as PFR. Kalau mixed flow reactor, well mixed flow reactor can be modeled as a CSTR. Oh, lagi satu. A over V here. What is A over V? Of course lah sebab dia drop and bubble. A over V equal to surface area of spheres 4 pi r square divide with 4 over 3 pi r cube. So yang ni pun sama. Okay, kalau model SCSER sama juga A over V 4 pi r square per 4 over 3 pi r cube. Multiply with dA. dA value given 10 negative 5 r. You have the diameter of drop. So dia jadi 0.05. CA in liquid phase. Concentration of A in liquid phase can be calculated because you have the initial concentration 2 moles per liter and then conversion 90%. So the remaining A 90% kali 2 1.8 0.2 moles per liter CA. CB not 1 mole per liter minus CB 0.9 multiply with 1. Dapatlah CB in liquid phase. And then you will get the residence time ataupun space time tau value. Lepas tu you can calculate the volume of reactor required. But remember, tau yang you kira dekat sini tau in liquid phase. Okay, yang ni semua in liquid phase. So you need to know what is the total volumetric flow rate when you want to calculate the volume, okay, total volume V equal to tau L, tau yang ni multiply with total volumetric flow rate. Total volumetric flow rate. Total volume.
Pada conteng
Bawah sekali, tak nampak?
tak ada. Tak nampak.
Sekejap. Draw. Okay, so tadi yang dekat sini nampak, yang saya cakap tau L ni nampak? Ni.
Sebenarnya tak
slide
nampak.
lain ya, madam.
Kena conteng slide lain
Oh.
Okay. Okay, untuk yang CSE yang kita model CSTR tadi lagi, okay? So, untuk jawab soalan B tu, tadi saya conteng CB naught. Ini semua in liquid phase. CB per tau equal to A over V dA per R CA in liquid phase. So, term yang belakang negligible. And then A over V sama dengan 4 pi R square. Ni nampak tak? Tengah tulis ni.
Tak nampak, madam.
Sekejap.
Tak nampak.
Pi R ni. Share lagi sekali balik. Kenapa dia asyik hilang MS Team ni?
Madam tengah share yang PDF punya madam tadi.
Lah, patutlah. PDF tu dah lama ditinggalkan sebab soalan yang sama. Jeng. Ni nampak?
Nampak.
Nampak, madam.
Tak ya. Okay, tengah nampak. Alright. So, soalan yang masih di soalan well mixed tau. Well mixed emulsion reactor ni. Okay, tak habis lagi. So, yang tadi ni saya conteng tak nampak lah ya.
Yang dekat soalan tu nampak ni. Ni.
Okay, so yang ni. Okay, yang ni semua yang you kira ni semua in liquid phase. Okay, so dA given, radius given, A over V equal to this equation ni, substitute masuk sini. dA 10 power of negative 5. CAL equal to CA naught 1 minus X, conversion given. CBL, CB naught yang ni given. CA naught given. So tak ada masalah. CBL, CB naught 1 minus X. X dua-dua 0.9. So sepatutnya tak ada masalah lah untuk kira all the unknown value. So you need to calculate tau L. Okay, tau L from this equation lah. Okay, bila you dah insert all the unknown value and given value, you can calculate residence time. And finally, to calculate volume, determine volume. Okay, volume equal to tau L yang you kira daripada sini tadi, from this equation, from this mass balance equation, multiply with total volumetric flow rate. Okay, total volumetric flow rate based on the given value. Kenapa keluar Bukit Raja bagai? Okay, yang ni daripada sini total volumetric flow rate. So kena hati-hati bila insert the value of total volumetric flow rate. The flow rate of aqueous phase 9 liter per minute. Flow rate of organic phase 1 liter per minute. So you mesti akan fikir which one. So kalau total volumetric flow rate 9 plus 1 for both. Okay. So total volumetric flow rate tau L multiply with V A naught plus VB naught. So maksudnya 1 plus 9, 10. So this is the total volumetric flow rate. So dia tak boleh masuk only one value. So jadi salah lah, dia kena masuk both value untuk dapatkan ni. Because we consider the reactor volume is total volume including gas and liquid. Okay, so itu sahaja contoh. So kalau untuk multi-phase sebenarnya bubble column or spray tower is much simpler compared to falling film. Cuma we need to know the reactor can be modeled as a PFR or can be modeled as CSTR je. And then after that you need to know reaction limiting or mass transfer limiting. Okay. So, kalau soalan yang ni dia tak ada pun minta the assumption of reaction, but usually the question will ask you what are the assumption of reaction. So, the assumption of reaction satu tadi macam saya cakap, tengoklah dia punya sistem can be model as apa? Can be model as CSTR or can be model as PFR. Itu satu assumption. Next assumption, reaction occur in which phase? Gas phase ke liquid phase? Ataupun contoh soalan yang ni dia dah bagi dalam soalan. Reaction control by the by the mass transfer of A from the organic phase. Itu the second assumption. Okay, which one is limiting? So yang ni mass transfer limiting. Mass transfer of A limiting the reaction. And then reaction only occur kalau the gas atau liquid. Reaction only occur in gas phase atau only occur in liquid phase. So usually we will have three assumption when the reaction involve multi-phase reaction. So again, model as apa? Model as PFR or CS star. The first assumption. The second assumption, reaction is limiting by reaction ke ataupun mass transfer of apa? Reaction only occur in liquid phase or only occur in gas phase. So, tiga assumption. Usually, we will write when we design the multiple reaction reactor. Dah dapat tiga assumption tu barulah you proceed. Usually, you need to write the mass balance equation. So, kalau it can be modeled as CSTR, so this is your mass balance equation. Yang ni. So, this is the mass balance equation if the reaction can be modeled as a CSTR. Kalau can be modeled as a PFR, this is the mass balance equation. So, R ni bolehlah ganti masuk negatif di CA over DT. Tambah lagi. Okay. So this is the mass balance equation. After dah tulis mass balance equation, next you kata this term can be negligible. So simplifykan the equation and then solve the design problem. Okay. Macam ni. Okay. Solve the design problem. Then you calculate lah apa unknown value. Kalau given value, just insert into the equation. Calculate the unknown value. And then after that, solve the design problem. Dia nak apa? Dia nak volume or dia nak residence times. So that's all. So bubble column memang simple. Kalau falling film, dia ada banyak case. So falling film saya dah bagi ada 3 contoh. Tiga-tiga saya ada bagi video dia in ni dalam MS Team. So you can watch the video. So before we end the session, any question? Tak ada soalan? So kalau tak ada, on Thursday, we will start with the new chapter, the last chapter, chain reaction. So, and then because we already done with chapter 1 and chapter 2, so I hope you can proceed with your assignment 2 because assignment 2 they related chapter 1 and chapter 2. They related to chapter 1 and chapter 2. So we are done with chapter 1. We are done with chapter 2. So I hope you can proceed to solve the question for assignment 2. And the assignment is in group. So sepatutnya lagi senang untuk you dapatkan the reference, lepas tu solve the design problem. So saya dah cerita how you can solve the design problem tadi. You need to make an assumption. Okay, barulah you boleh solve the design problem for multi-phase reaction. Okay, so if you don't have any question, okay, we stop until this part. We stop until here. Dah habis. So you also can try to solve another. Tak ada lah soalan. Semua saya dah tunjuk dah how to solve the question yang ada dalam nota ni. Okay, except this one. Yang ni soalan example in textbook. So you can find the solution in the textbook untuk soalan yang ni. So the rest semua saya dah tunjuk on how to solve the problem except this mana ke yang tadi? Ada satu soalan except this one. Sebab yang ni quite complicated. Ini kena buka buku ni sikit lah untuk you kira at STP condition. So yang ni je yang ni. Beza sikit on how to calculate the value. Tapi soalan B ni sama macam contoh-contoh yang lain. Okay, ni tak ada masalah. Except question A ni je lah. Okay. So yang lain semua saya dah tunjuk, semua saya dah guide macam mana nak solve the problem. Right. So we meet again on Thursday. Okay. And we will learn the new chapter, chain reaction. So see you all on Thursday face to face. Okay. Assalamualaikum and thank you for your time.
Waalaikumsalam. Thank you, madam.
Thank you, madam.
Thank you,
Thank you,
madam.
madam.
Thank you, madam.
Okay.
Thank you, madam.
Well mixed and